Hello everybody, this is the electrical engineer here, CB 455 New Jersey, Ham WA2RCC, Royal Crown Cola, base station Fair Lawn, New Jersey, and email vicmiller1@aol.com. I am now making a video instruction for CB linear amplifier enthusiasts. I've noticed that there's been a lot of interest in understanding how the circuit of these large multi-pill amplifiers work, and I'll be giving a full explanation of that today. This is kind of my way of paying it forward after a lifetime 45-year career as an electrical engineer. So let's begin. We're going to be covering the important principles, and we're going to be doing some learning today about large linear amplifier circuit design and operation. Okay, so what we see here is a two-pill amplifier drawing. Let's take a look at that. You see the two transistors. You see an input and output transformer, which we're going to get into. Let's take a look at another one. Here's a four-pill amplifier, classic. And we notice already that the amplifier is built out of two-pill sections. I've outlined one of them here in yellow. There's another two-pill section just above it here. Let's look at a different amplifier. Here's an 8-pill, and we see four two-pill sections. You can easily recognize them. We can see, as I've shown here with the yellow highlight in the yellow box, an input circuit, the two transistors side by side, and the output circuit. Here, the output transformer. Let's take a look at another amplifier. This one is a 16-pill. We can see here 8 two-pill sections. I've outlined them in yellow. You can see each one is built the same. Each section is built the same. They all have the input transformer, the two pills, two transistors, and the output transformer. And even the big, massive, giant 32-pill design is again made up of two-pill sections. So what we see is the common theme in all these designs is the classic two-pill section. It's a push-pull transistor amplifier section, and in order to understand the operation of these CB linear amplifiers of this style, we need to focus in on the two-pill amplifier push-pull section. We're going to get into important detail of how this actually operates. Okay, so in order to analyze the very important, fundamental, common two-pill amplifier, linear amplifier push-pull section, we need to have some basic principles very quickly. Here we have the idea that the supply voltage, we're just going to call it a supply voltage, this is typically your 13.6 volts, is going to always travel from the high potential down towards the ground, 0 volts. So you can think of it here on the right as a waterfall. The electricity, the potential is always going to flow downwards to the lower potential. Okay, so a quick review of the diode operation, which is a basic PN junction. It's drawn here as the anode and cathode. You can see the triangle and the line. That's the diode symbol. And the basic operation of the diode, as shown in this drawing, is basically one-way electricity flow from the positive to the negative, as shown here. And we can see that a typical 27 megahertz CB frequency sine wave, which is our carrier signal coming from the radio, would be allowed to flow through the diode and produce positive pulses only. Flow the opposite direction is blocked, by the diode. The diode is a one-way valve, a one-way conductor, only when the anode is positive compared to the cathode. We have to have a positive voltage on the anode side compared to the cathode to get current flow through the device, as shown by this plus and minus. So again, the diode is a one-way valve, and the reason we cover this now is this is important in understanding our next chart, which is how a transistor works. Okay, so here we see a diagram of the basic amplifier transistor, the classic NPN bipolar. We see a picture in the upper left there, the 2SC2879, and we can see our old friend, the diode, as shown from the base to the emitter. So a transistor of this type behaves as a diode from the base to the emitter. And the way it works, we just covered the diode before. If there's a positive voltage on the anode compared to the cathode, so the base to the emitter, if that voltage is positive, as shown by the plus and minus, we will get positive flow into the transistor, as shown by this light blue arrow right here. And what happens, there's a lot of physics involved, but what happens inside the transistor is there's a transition of a field, and current starts to flow from the base to the emitter, just like a diode. And what that does is it opens a channel, basically, of visibility of the supply. Remember, the supply voltage wants to go from the high potential down to the ground. When current starts flowing from the base to the emitter through the diode junction, it opens a pathway to allow the higher potential supply voltage to see the ground terminal, and a strong current will flow from the supply through the collector, as shown here, pulling in towards the transistor, which is why I've drawn it as a little dipping curve, and down to the emitter. So a small voltage, small current flow from the base to the emitter allows a much more large, massive current flow from the supply, the collector, to the emitter, as shown by the heavy blue arrow. And that is what allows the transistor to control the flow of electricity, and also produces gain, amplification. The current flowing in the main collector path is many times larger than the original starting current, or the control current from base to emitter. And so that's expressed here, that the current in the collector is a gain, a multiplier, G, times the original base current, and that gain in power gain is approximately 30 times bigger in power gain. And so that means a 1 watt in will give 30 watts out, or more like 3 watts in will give 90 watts out. So that's how the transistor operates. A small control current from the base to the emitter allows a much more massive current flow in the main path from the collector to the emitter. Okay, so I've just explained that the main current flow, like a waterfall, is going from the high potential V supply down through the transistor, which is turned on by the base to emitter positive junction, and to ground. However, we're not going to just let the current flow straight to ground. We're going to actually get useful work from this current flow by putting a load in the path from the supply to the transistor to ground. And that's shown here. You can think of it as a water wheel. It's a waterfall flowing down, and it's creating work as it goes over the water wheel. The same thing is happening when we pass the current through the load, through the conducting transistor to ground. Okay, so now I've drawn two instances of our transistor setup, and they're mirror image of each other. You can see the mirror image is dotted center line. and the two transistors are arranged in a mirror image configuration. And notice that both of these transistors have a path, again a conducting path through the transistor from the supply to the ground. In the upper section it's flowing down the page. In the lower section it's flowing up the page, but it's still flowing from a higher potential, which is the supply, down to ground. So we have to imagine that, and it's a mirror image. There's two conducting paths, both from the supply to the ground, with these two mirror image transistors. Okay, so now continuing, notice all I've done is redraw the previous diagram, and what I've done is instead of the supply and the load coming from the top and bottom portions of the page, I've wrapped them around, and now you notice the two supply points are right next to each other, and they actually represent the same high potential circuit point. So in future drawings we're going to connect those two. It's one single common supply voltage point. And also notice on this diagram that there's two different paths that current can take from the supply voltage to ground. If the upper transistor is turned on with a positive to negative base to emitter junction, remember our diode, if the diode turns on, it will allow strong current flow through the transistor, and it'll go from the supply around and to the ground. On the other hand, if this transistor is turned on with a positive voltage from the base to the emitter, again the diode, our friend the diode, that will turn on the transistor and allow a strong current flow to flow from the supply around through the transistor and to ground. So there's two different paths that the current can take from the supply, high potential, down to ground, depending on which transistor is turned on. And we're going to see, depending on our input signal, these transistors are going to take turns alternating, each one at a time, alternating their paths to ground. So sometimes the current is going to flow through the upper transistor to ground, and other times the current is going to flow from the lower transistor to ground. But in both cases, it's going from the higher potential to the lower potential through the load, two different loads here, as we see, and a common supply point. Now I'd like to introduce a very important circuit component in the design of the multi-pill linear amplifier, CB linear amplifier, and that is the center-tapped RF transformer. This is a simple circuit design of our center-tapped RF transformer. The diagram on the left side is showing an input. This is a cycle of our 27 megahertz CB carrier. The green is positive, the orange is negative, and we see that it goes through the primary of the transformer, creates a field across the air gap, and induces a voltage in the secondary winding, as shown here. And that secondary winding is center tapped to ground. Okay, and let's look at the voltages that occur. We see when the signal goes positive, we create a positive voltage across the whole winding of the secondary. So from the upper arm to the center point, it's going positive, and from the center point to the lower arm, it's still positive, because the overall voltage across the secondary is a plus to a minus, the whole winding. Now that's measured from each arm, from the top to the bottom, and then again from the top to the bottom. But if we measure that same voltage on the diagram on the right, if we measure that same voltage from the outer arms to the center tap point, what we see is the positive going voltage in the primary creates a positive voltage across the whole secondary, and therefore, as measured from the upper arm to the center point, it's still positive, but now measuring the opposite way from the lower arm to the center point, we see that it's actually a negative voltage relative to the center tap point. And so when the upper half of the winding goes positive relative to the center tap, the lower part of the winding, the outer arm, is actually going negative compared to the center tap. So they're inverse, they're opposite of each other. When the upper one goes positive, the lower section goes negative relative to the center point, and when the upper one goes negative, the lower half of the winding will go positive, as measured from the outer arms to the center tap point, which is ground, which is the neutral. So this is a key concept. The center tapped RF transformer is creating opposite voltages from a single-ended input. We're looking at the diagram on the right side, and so there are opposite mirror image voltages being produced from one input. And that's why the center tapped RF transformer is creating a single-ended to a balanced pair of voltages which are in opposite phase, 180 degrees out of phase, or opposite polarity. When one is positive, the other is negative. When one is negative, the other is positive. Alright, now we also see, I've redrawn the center tapped RF transformer to show it as an output transformer. Notice in this case, we're going to gather up to one single-ended output the balanced center tapped current flows from two circuits here, two paths, which will be our two transistors in the diagrams that I showed earlier. You can see that the upper transistor will create a current flow this direction, which will induce a positive voltage across the air gap and into the secondary, positive pulse. And in this flow, going the opposite direction, we can see that since the flow is in the opposite direction, the voltage set up across the primary and the secondary will be in the opposite polarity, negative. So we're able to take two different paths through a center tapped RF output transformer and create a single carrier sine wave at our CB frequency 27 megahertz in a single-ended output. So again, this is the output use of a center tapped RF transformer. Now I'd like to show the very important implementation of the center tapped RF transformer. I have a number of drawings here to help us understand how this center tapped RF transformer, which you can see the circuit diagram in the upper middle, how this is actually implemented. And this is, though, one of the key technologies of the RF CB linear RF amplifiers. So we see in the upper left the use of copper tubes and some end plates. And it's very important to understand the end plates on the one side of the copper tubes are isolated from each other. There's a space here, as you can see, but the other end of the copper tubes is attached with one solid end plate. And this has the effect of creating a conductive path. This is going to be our center tapped winding, as you can see here. The circuitry is an end connector. The outer end of the winding goes up through the copper tube, across the back plate, which is one continuous conducting piece, which is the center tap point, and then out to the other end. And so this creates an end, a center tap, and the far end, one single winding, which I've drawn here. There's a copper tube inside this ferrites across the back plate, which is conducting one solid piece, and then out to the other end, winding end. So it's one turn with a center tap on the back plate. Here's a picture of the back plate, and you can see it's all one continuous piece. And so that creates one turn, one center tap turn on the center tapped winding, as shown here. And then on the secondary, the output side, single-ended, we have the secondary winding, which is going through the air gap. There's an air gap here, which is the separation between the center tap winding and the secondary single-ended winding. This is the secondary winding, which normally is grounded on one end, and the output single-ended is taken off the other end. Here's one drawing of it. Here's another drawing. Again, there's copper tubes which connect to a solid end wall and out the other side. That creates one center tapped winding, and then the secondary goes through the air gap through the copper tubes. Now this technology, this architecture, this structure is used both for output transformers and input transformers. So let's take a look at how this is implemented in the classic two-pill linear amplifier stage. Also, I just want to mention that when the center tapped RF transformer is implemented, we'll notice that the output transformers are usually physically larger than the input transformers. This is because of the amplification, and therefore the field strength and the signal power is greater on the output side. So larger ferrites for greater power handling capability. I just want to mention that some of the good old boys still refer to these style of transformers as stack-pole transformers. That name comes from the vendor, Stackpole, that made the ferrite beads for these. But we're going to use a more meaningful name. We're going to call them ferrite RF center tapped transformers. All right, just a quick recognize to the original engineers that came up with the RF center tapped transformer design that I've described, with the copper tubes and the ferrites to make a center tapped winding and a single-ended secondary winding. Really brilliant engineering there, and kudos once again to the great engineers at Motorola. This is a picture of some of those early papers. It goes back to the mid-60s, 1960s, and so on. Okay, folks, so we're almost home here. We're in the home stretch. And what I've done, this is an important drawing. I've revisited our classic two-pill push-pull amplifier stage in the photograph. And what I've done is a circuit overlay, understanding all the circuit components that we've already covered. I'm going to take us through the actual layout of this circuit and how it looks, and then we're going to analyze the operation of the classic push-pull stage. So we see on the left the input RF ferrite transformer. Remember, the winding going through the air gap is the single-ended. That's the brown wire here that we see. That's the input winding. And then we know that the copper tubes, which go through the stack pole, through the ferrites to the solid back wall, which is the center tap point, and then back out through the other copper tube connecting to the two transistor bases, is the one-turn center tapped winding, as you can see here on the input transformer. Then we go through our mirror image push-pull transistors. The emitters are tied to ground, and we're going to see each of these transistors will turn on when their base voltage goes positive relative to ground. The output, here's our load, the output collector, and our supply, which is actually coming in on this red wire. There's an RF choke here picking up the DC supply, our voltage supply, going to the back wall, which is the center tap point of the output transformer. The copper tubes going through underneath these ferrites represent the load. It's a single turn center tapped, which is our center tapped winding on the load side. And then this white wire here, which you can also see over here, wrapping through the air gap on the output transformer, represents our secondary winding. It's single-ended, which is our output, shown here in the circuit diagram. And we're going to see shortly that again we have a single supply with two paths to ground. It wants to go from a high potential to ground. It can either go this way through the upper transistor or this way around through the lower transistor. And we're going to see that these two transistors are going to be alternating for each half cycle of our input signal. So now let's go back to a circuit diagram and understand the operation of this implemented push-pull amplifier stage. So here we have it, guys. This is the big complete circuit diagram for a full two-stage linear amplifier stage. Let's go through the circuit operation. We see on the left side the input when we key our transmitter. Cycles of RF carrier start to come in. Goes single-ended input here on the left, which creates positive and negative going cycles on the center tapped RF transformer, measuring the voltage from the outer arms to the center tapped point, which is grounded. We see alternating positive cycles on each side of the center tap. So the first half cycle, shown in green here, will turn on the upper transistor. Because of the base to emitter, we have the diode. It's going positive. It starts to conduct and therefore creates a path for the supply voltage, which is at the high potential, to flow around and through to ground through the upper transistor, creating a positive going large amplified pulse here. On the next half cycle, the lower arm is positive compared to the center tap. The upper transistor is off, and now the lower transistor sees a positive from the base to the grounded emitter, creating flow here, and therefore opening the transistor, allowing the larger current to flow from the higher potential supply through the lower arm, through the transistor, and creating a strong amplified negative going pulse here. And then these alternating cycles of current going through the upper half of the transformer and then alternately through the lower half, they're flowing in opposite directions. So that creates opposite poles of the output, single-ended output. First we have a positive going pulse on the upper half flowing upwards, and then we have a lower negative going half cycle because of the flow in the opposite direction on the lower half of the center tap transformer, inducing through the air gap, inducing a large amplified carrier cycles in the single-ended output. So that's how the circuit works. Each half cycle is flowing through one of the two transistors. First the upper transistor to ground from the high potential, and then the lower transistor from the high potential to ground. And because of the center tap transformer, the flow is in opposite directions, creating alternating field, going positive and negative, recreating our carrier, but amplified, so we have power gain at the output. And then the combination of many of these two-stage push-pull, this is called push-pull amplifier stage. The combination of more of these stages adds their power together because they're operating in synchronization. They have to be operating in sync so that their powers are adding from all these stages. That's called the RF combiner. We're going to go through that in another tutorial, and also we'll be covering the keying circuits and so forth. But here you see a good drawing of the operation of a two-pill push-pull amplifier stage, linear amplifier stage, for greater output signal power. Okay, folks, so there we have the full explanation of the two-pill CB linear amplifier push-pull amplifier stage. Hope you've enjoyed this tutorial. This is 455 New Jersey, in the Garden State. Ham radio WA2RCC, Royal Crown Cola, Base Station, Fair Lawn. Contact vicmiller1 at AOL.com. And keep in touch. It's all the best regards. 73s.